Okay, so we're going to start out with thermodynamics and the kinetic theory. Now, before we talk about the kinetic theory, the study of thermodynamics is really just a study of heat transfer. The kinetic theory is a theory that attempts to explain the effects of temperature and pressure on matter. The kinetic theory is a model, and it helps to explain phenomena that occurs at the molecular level where we can't see what's happening. And it's a way of simplifying some of the complex interactions that occur with molecules. And it helps us to kind of visualize what's happening at the molecular level. What do you think the word kinetic implies about the kinetic theory?
That it's moving, like molecules that are moving.
It has something to do with moving molecules, or molecules that are moving. Yeah. The kinetic theory's got three postulates. These postulates, these are statements that are assumed to be true in order for the kinetic theory to work. Okay, so these are statements about our model. In order for our model to work, these statements need to be true. Okay, the first one, all matter is composed of small particles. Now that works whether you're visualizing atoms or you're visualizing molecules. Second postulate, all particles of matter are in constant motion. In fact, in chemistry, you studied a temperature that is a theoretical temperature. It's never been reached in the laboratory, but it's the only temperature where there is no movement. Remember what temperature that is?
Absolute zero.
Absolute zero, absolutely. Absolute zero. 0 degrees, or I'm sorry, I said it wrong. Zero, what's the unit?
Kelvin.
Kelvin, 0 Kelvin. I say that all the time. I always say 0 degrees Kelvin, but that's improper. If you want to sound really smart when you go to college, which you are smart, but if you want to sound really smart, then When you state a temperature in Kelvin, don't say degrees, because it's not degrees Kelvin. It's 0 kelvins. Now, if you state it in Fahrenheit or in centigrade or Celsius, it is degrees. But if you state it in Kelvin, it's just kelvins, because all those scales are based on kelvins. All particles of matter are in constant motion unless you're at that theoretical temperature. And then the last one, the motion of particles causes random collisions to occur. These collisions are perfectly elastic. Okay, now we just studied elastic collisions when we were studying momentum. And one of the things that you found was that in a perfectly elastic collision, there is no loss in kinetic energy. The kinetic energy before the collision of all the particles equals the kinetic energy after the collision of all the particles. And so we can say no kinetic energy is lost. Now, how is kinetic energy lost during collisions? Well, one way is sound is released. When you have two cars and they run into each other, you usually hear braking noise, crunching metal, breaking glass. That's all energy being released. Also, when you deform metal, you've got to rearrange the molecules to do that, and so they might be closer together. So you might change the internal energy of the material by compressing it. Also, the energy probably heats up as you bend the metal. It heats up a little bit. You lose energy that way. Well, these perfect small particles, they don't deform. In fact, if you think about it, they actually never touch each other. They are kind of like magnets, and the electric magnetic forces, when the two molecules get close together, they eventually repel each other. When electrons get close together, they repel. So they can get just so close, and then they're repelling. You actually don't have like electrons hitting electrons, and you have like gap in between. There's always gaps in between the particles. Okay. So there are three phases of matter which you've studied, and so we're just going to go over that briefly. And we're going to talk about three phases. There are actually four. There's solid, liquid, and gas, and you know that there's also plasma, right? In fact, plasma is the most abundant phase in the universe. More things are in the plasma phase than any other phase. But here on Earth, plasma is not the most abundant phase. And so we're going to leave plasma out. Plasma is a superheated fluid gas that is it's so hot that the electrons have been stripped off of the atoms, and so they're ions. It's an ionic superheated gas. And so the stars are composed of plasma. And they have other forms of matter too, but they're primarily composed of plasma. Okay, so on a solid phase of matter, you have low kinetic energy of particles. Now this is at the molecular level, at the particle level. Liquids the liquid phase, it has enough kinetic energy to overcome the particles' attraction. So particles have an affinity for each other. Water molecules attract other water molecules. And so these forces, these intermolecular forces, they have to be overcome so that the solid phase, the particles in the solid phase can then move around each other. Yeah.
Can I ask a question?
Yes.
So on solid, you said low kinetic energy for instance. Aren't the particles in the solid moving a lot faster? Aren't they moving a lot faster against each other than liquids and, you know what I mean?
No. No, solids in general, for a given material, okay, you got to talk about the same type of atoms or same type of molecules. Solids have less kinetic energy. The particles have less kinetic energy than a liquid of that same material or a gas of that same material.
So they're not moving at a higher.
No, they're not. No.
I always thought that.
All right, so liquids, they have enough kinetic energy to overcome the particle attractions. We're going to call those later intermolecular attractions. Particles move around but don't escape the group. And then the last phase that we're going to talk about is the gas phase. And in the gas phase, we have enough kinetic energy to break free of other particles. Particles spread out and fill container. Okay, so let's draw a diagram. We'll draw like a beaker with solid, liquid, and gas. And this will all be the same matter. Here's our beaker. And of course, if it's a gas, it'll either have to be heavier than air, or we'll have to have a lid on it. Okay, so here's our three, and this is going to be solid, liquid, and gas. And for our solid, we're just going to show. I'm going to have a diatomic molecule there, so two particles. But because it's a solid, they're all not next to each other in some array. Okay, it might be if it was a crystal type structure, it would be like a lattice. But in some form, in some shape that these particles typically line up in. In a liquid, we have our molecules they're moving around each other. So I'm trying to draw some little arrows, but it's not working. And then in a gas, the particles break free of each other. And they fill the container.